Hello everyone, welcome to course study on solid mechanics. In today's video lecture, we are going to see the shear stress distribution in a rectangular cross section of the beam. For that purpose, you concentrate on a rectangular cross section of the beam A, B, C, D. It has width equal to B and depth equal to D. Therefore, assume one layer EF at a distance of y from the neutral axis of the beam section. So in that particular rectangular section, we have concentrated on section any layer EF which is at a distance of y from the neutral axis. B is equal to the width of the rectangular section. It is already shown in the figure. This is B. D is equal to depth of the rectangular section. This is D. NA is equal to neutral axis of the beam section. This is NA, which is the neutral axis. EF is the layer of the beam at a distance of y from the neutral axis of the beam section. This is layer EF at a distance of y from the neutral axis. And remember that y bar, very important concept, y bar is the distance of CG of the area CDF from the neutral axis of the beam section. Now, as we have concentrated on section EF, we have to determine the value of shear stress above that particular section EF or below section EF. We can choose any section which is above or below. Now we have concentrated on the section which is above layer EF. Therefore, y bar is equal to the distance of CG of the area CDEF from the neutral axis of the beam section. Now, as derived earlier, we have shear stress formula tau is equal to FA y bar upon IB. Now we are going to derive one term one by one. First of all, we have F as it is. We are going to find out the value of AY bar. We are going to find out the value of I also. We are going to find the value of B also. Now first of all, we will find out the value of area A. Therefore, consider the value of area of the section where shear stress is to be determined. Therefore, area will be given by width B into d by 2 minus y, because we have width equal to B. All of you know that for a rectangular section, area can be given by width into depth. Now width will be B and depth can be calculated by this manner. The total depth of rectangular section is D and half of that particular D will be the d by 2, and for this particular depth the answer will be d by 2 minus y. Therefore, we have area is equal to B into d by 2 minus y. Distance of CG of the area CDF from the neutral axis of the beam section y bar could be given by as follow. Now we have to calculate the value of y bar. First of all, we have to determine the value of shear stress for a rectangular section. In that, we have F as a constant value. We have find out the value of A. Now we will find out the value of y bar. Y bar can be given by y plus d by 2 minus y whole upon 2, because y bar will be this distance. This distance is nothing but y bar. Therefore, it can be given by this y plus half of d by 2 minus y. This is our y bar, and this y bar can be given by this y plus half of d by 2 minus y. Therefore, we will have final equation y bar is equal to d by 2 plus y whole upon 2. Now we have find out the value of AY bar. We are going to find the value of I about the centroidal axis. Therefore, the value of I about XX axis through its CG can be given by BD cube by 12. Therefore, on putting the value of AY bar, the value of F and I into this equation, I have final equation tau is equal to FAY bar upon IB. Therefore, tau is equal to F into we have a is equal to, we are going to put the value of a also and y bar also. We have a is equal to b into d by 2 minus y. That value we have put into this equation. Now y bar will be d by 2 plus y whole upon 2, and that value we have put over here. Therefore divided by I will be bd cube by 12 about the centroidal axis, and b will remain as it is. It's a width of the beam. After rearranging the equation and solving mathematical expression, I have final term is equal to 6f into bracket d by 2 bracket square minus y square and whole divided by bd cube. This is the value of shear stress at a layer EF. Remember that this is the value of shear stress for a layer EF, and as we know that shear stress is a function of distance y. When y is equal to 0, that is at neutral axis, we will have the maximum value of shear stress. If you put the value of y is equal to 0 into this particular equation, then we will have tau maximum, and that tau maximum will be 6f into d by 2 bracket square upon bd cube. This is the value of maximum shear stress when y is equal to 0, and we will have y is equal to 0 at the neutral axis. Therefore this is the value of maximum shear stress. But if I put y is equal to d by 2 into this particular equation, then I have shear stress is equal to 0. Remember that the value of shear stress is a function of y. When y is equal to 0, that is at neutral axis, we have maximum shear stress, and when y is equal to d by 2, that is at extreme fiber, we have shear stress will be 0. Therefore after putting y is equal to d by 2 at top or bottom, the shear stress will be 0, and y is equal to 0 at neutral axis, the maximum shear stress will be 3 by 2 f upon bd, and all of we know that 3 by 2 is nothing but 1.5 into f upon bd. Now f upon bd is nothing but it's a force upon area. Remember that f upon bd is the force upon area. Therefore force upon area is nothing but it's a shear stress, and that will be the average shear stress. Therefore we will have tau maximum is equal to 1.5 into tau average, where tau average is equal to shear force upon area, which is equal to f upon bd. Therefore from this equation we can say that for a rectangular section, the value of maximum shear stress will be equal to 1.5 times the average shear stress. From this equation we can say that the maximum shear stress will be the 1.5 times of tau average. And from this equation you can see that we have y square over here. Again, as the shear stress is a function of y, and as the power of y is 2, therefore the shear stress variation will be parabolic in nature. Therefore for the rectangular section we have shear stress variation in a parabolic manner, and that will be maximum shear stress at the neutral axis when y is equal to 0, and minimum shear stress at the extreme fiber, that is when y is equal to d by 2. Therefore from this statement also you can concentrate on this statement also. Shear stress distribution is parabolically across the rectangular section. Shear stress will be maximum at y is equal to 0 and will be 0 at extreme end, that is when y is equal to d by 2. So in this manner we have determined the value of shear stress distribution across a rectangular section. In the next lecture we are going to discuss the variation of shear stress for a different cross section of the beam, that is for a I section, for a rectangular section, for a circular section, for a T section, or for the plus sign also we are going to derive the shear stress distribution. So we will stop here. Thank you.